Welcome back, chat. Cool. Today, we are going to jump in Precalc, and we are in lesson 1.7.
Oh. I knew I was going to say that.
Oh, I missed a golden opportunity. All right, 1.7, our focus today is going to be on transforming functions. 1.6 was apparent functions, which, thank you guys for not making me write all that super boring throughout the day. Cool. Hopefully it was better than if we'd had written. All right, anyway, transforming functions. So all I really care about is how do we change them. So first thing that we're going to do is going to look at some nice ones. So I've said so about 1 million times. Therefore, am I having deja vu with you guys, or is that a last year thing?
What?
There was a class where I realized how frequently I was saying the word so or K, so I started to say other stuff, and then that other stuff just happened. Yeah, okay. I believe you. I no recollection. I know it's happened, don't know with whom or when. Okay. Today, transforming functions, all that we're worried about is given, and this is a weird bullet point, but we'll deal with it. Given f of x, we can also graph h of x that simply moves f. Now, I will call it f of x here. When I say it moves it, there's only a few different operations that we're really worried about happening. When I move a function, I can move it left and right. I can move it up and down. I can reflect it. Have I changed anything other than its orientation and location? Are there things that I can change that will take my parabola here and make it this parabola or this parabola?
Yes.
So those are non-rigid. They change the actual shape, sort of. I would say they change characteristics of the shape, but if it was a parabola, it's still a parabola. It's either thinner. I thought we just heard thunder, which was not prepared for. All right, so with this notation, here's kind of an example of what I mean. If we take a function, f of x, and just say it's some function, is a function. And we can do this in general, but we will use the board to help us in Desmos. F of x is a function, then if I define h of x as, I don't know, maybe something awful like a times f of b times x minus h plus k. Just like we saw in the bell ringer. I'm just defining h of x as adding something additional to my other function f that we started with. So if we add all of this, then this thing moves and changes the graph. Throughout the next 20-ish minutes, 30 depending on how quickly we can all make sense of stuff, I just want to know exactly how does each of these things change the graph. So there are some easy ones that we can use, and there are some hard ones that we can use. Let's get in real quick, and I'm going to use a tilde for each. What letter would you like to start with? Okay, so this one, A, and I have a dumb way that I remember it, but I remember that A is for also orientation, and shape. Now, there will be a little bit more to this here in a minute, but orientation and shape. When I talk about orientation, I just mean happy parabola, sad parabola. They could be the exact same, and they've just switched the orientation. Which way do they open? When we go a bit further into this, this is a type of non-rigid. It just means it changes the actual shape. So here we go. Do you want orientation? Let's do orientation first. Okay, if a is less than 0, then h of x will reflect f of x somehow. And I want to know how. Okay, I don't care which function we actually draw on the board. It could be any function as long as you can draw it and graph it nicely. Quadratics are really easy to see stuff happening. Anybody opposed to me just using a quadratic? Okay, so let's pop over to Desmos real quick. And let's dig in. And we're going to define it exactly like I am here because it's weird to see the H stuff if you've never seen it. Okay, where's the vertex going to be for the regular parent? So if I said x squared, 0, 0, hey, it is. Now if I define h of x as a different function, and I just let it be a times, and I'm going to change this, let's try 3f of x. What did it do? Red is original, blue is the new one. So everybody looks and they think it's compressed. I think it's stretched.
Oh.
Now, yep, if like this is always weird, here's the strangest part. You can never tell for sure if I just give you this graph. You can't tell me if it's been compressed or stretched. Not directly. Did anybody see where I put a big thing of rope?
Over there.
It's on my desk.
Yeah.
So,
Oh.
no, you're good. Jump rope my way up there real quick. I'm not really gonna. I bet I could. All right, check it out. Is this table gonna hold me if I stand on it?
Yeah. Let's see.
Okay.
I'm gonna find out.
If I fall, you can laugh, right?
Yes.
But if I'm like bleeding and stuff, what are you guys gonna do?
Call the principal. Oh.
Yeah, or 911. You can use your phone, just so you know. Like if I, yeah.
No phone.
All right. So everybody agree that I have a parabola right now?
Yeah.
Okay, let's say here's F. Okay, if I want to make it thinner, there's two things that I can do. I'm holding these points right here on the edge, right? I can pull up. When I pull upward, here it is, relax. If I pull up, did it get thinner? Okay, so did I just stretch it or did I compress it? I stretched it, but here's the weird part. I can grab these same points and I can pull in. Did it get thinner? Did I stretch or compress that time? I compress. So if I stretch this direction, it gets thinner. If I compress this direction, it gets thinner. But they look the same on the graph, right? The first direction that we're seeing is what A is changing. Which direction? You said up. Give me another word. Vertical. So this part's more challenging. Okay. So if we're here, I can see it's gotten thinner, and there's our first little part. If A is less than 0, sorry, we'll deal with this. What if I make it negative? Where? Okay, it was across the x-axis. So check this out. If f of x is, or if A is less than 0, then h of x will reflect f across the x-axis. And I think that that's pretty clear when we're looking at it. Functionally speaking, it seems to make sense. Because if I say f of x, or f of 1 is 5, and I reflect it, then f of 1 should now be negative 5. It's just reflected down. It's got a negative in front of it. Hence the outside piece. Okay, then we get into this other weird part. I'm going to let this be a slider instead. So we'll just let it be numbers. And it's jumping by, I want it to jump by smallers. So let's say 0.1. Okay, so here I am. They're both the same. If it's 1 times f of x, they're the same function, right? What happens if I make this bigger? So if it's 1.1 or 1.2 or 2.3, we saw it a second ago. It got thinner. This number out in front, was that the vertical or the horizontal? Vertical. So as we're looking at this, we have to then consider not only the reflection part, but I'm going to use asterisks here instead so they don't look like minus signs. If, now I can't just say A is less than 1 because that covers like all the negatives and stuff. But if I say the absolute value of A is less than 1, there's one possibility. Or if the absolute value of A is greater than 1. Those are the only two possibilities that we have for changing a when we don't consider the negatives. Let's see. If a gets bigger and bigger and bigger, my graph gets thinner and thinner and thinner, which means in the vertical direction, stretched or compressed again? Stretched. So if the absolute value of a is greater than 1, then vertical stretch, then vertical, I'm just going to use vert, stretch. Now, there's some weird language in here that can be hard to think about. It is going to go by a factor of a, and that can be hard to view, but we'll say vertical stretch by factor of a. Where, and I'm just going to do this one on the board here. If I had x squared and then 2x squared, any y value that you would get, you would just double it. So that's our factor of 2 part. So instead of 1, 1, the point becomes 1, 2. Instead of 2, 4, I should probably just do it here. We'll make this 2, and we'll see exactly this. So 1, 1 is on this graph, right? What if I made it twice as tall? It'd be at 1, comma. Oh, okay, so it is. There's 1, 2. At 2, 4, what if I made it twice as tall? It'd be at 2. Hey, look, it is exactly there. We're stretched vertically by a factor of whatever a value we pick. Okay, on the flip side, what if a is less than 1? It's getting real sad, real wide, but we've just compressed vertically. So if a is absolute value is less than 1, then compress vertically. Do I have to say by a factor of a, or can we just assume that it's also there? Okay. All right. This is where it gets really weird. On these ones, vertical stretch, thinner or narrow. And then I think that steeper might actually be the word that I like to use, but it feels weird when we see it the first time. And this one would be wide or less steep. So many S's. It's weird to think about the steepness of a parabola, but if we thought about the linear function, here it is, right? Here's the y equals x. This is just my arm doing it. If I make it 2x, does it get steeper? X to 2x, does the steepness increase? For sure. And the graph would get thinner if you're looking at it there. It's weird when we look at it for maybe not a quadratic. Everybody cool with this? All right. So we dealt with orientation and shape. B is the next natural choice. We're going to skip it for a minute. Okay. Check it out. Let's jump to H. H is for horizontal translations, but that one doesn't fit in as well. Horizontal translation. Now, we're going to pick up little bits of language here that you'll hear me use all year long, this year, next year. I hope future teachers use it. If I give us a function like h of x or f of x, I said, what is the argument? Do you guys know what I'm talking about? So maybe that's a good thought. The argument, anytime that you see me use it, and I'm going to do it in pink here that you can ignore for a second. What am I taking the sign of in this situation? That's my argument. What am I taking the cosine of in this situation? So the argument of cosine here is what? X minus 1. It's just whatever is included. Now, we can use this isn't great language, but whatever I'm going to put in here of my square root, you could call it the radicand. That's like the formal language, but we could call it the argument as well. Okay, I will use that language over and over and over and over. So here's what we want to think about, and I'm going to see if we can't get it. Instead of doing just that, we'll let a just be 1 for now, and then let's add that h in there. So we'll go all the way to 1, and then I'm going to make this x minus h. And it didn't want a slider, so I'm going to do it b. What letter don't you guys use? It won't let me make h a slider, so you'll just have to let it be c for a second, okay? All right. So here we are. If it's 0, whoa, that's the wrong thing. If it's 0, I just get what? The same. this is where it gets super strange. This value, if I move it to the right, which way is my blue graph going to move? So like inside of my parentheses, it's x minus 2, for example. It goes to the right 2. Now, that's a weird idea to think about. When we're looking at these, all we have to do is look at the following. In our form, our original, it was x minus c, or x minus h inside your parentheses. Can you guys confirm that? X minus h, right? Okay. The h value, its value is what we care about. Only h. And we'll like clean that up a little bit. If, and I'm not going to write if, we're just going to use our fancy shorthand. If h is greater than 0, then do what? Move h units. What do you guys think? So if h, c in this example, because I couldn't use h, it moves to the right. If c is positive, it moves to the right. Move h units right. Now, there's some weird things in here, and we will work an example within here. What if h is less than 0, or a negative number? Move left. Where people get goofed up with this, and it's an easy, natural, like totally get it. If I say x minus 5, you move 5 to the right, because it's already written as x minus whatever c is. Okay, let's just see the value of these. So I'm just going to make a last little note. Inside argument. And what I mean by that is it's inside the parentheses, f of x minus 2, x minus 5, whatever the case might be. So here's my challenge for you. I want to just let f of x equal something. Let f of x equal, I don't know, let's make it a little bit crazier here. Let's say it's x squared plus x. And you might not have a great idea of what this graph looks like. That's okay. All I want you to do is describe, and then let's look at a couple of them. Now we're going to build up. So at this point, I'm okay to change the value of a somewhere, but I'm also okay to change the value of h. Those are the only two things that I'll possibly change. So let's let h of x equal, and I'm going to leave a blank space here very intentionally, but let's say it's x minus 3 squared plus x minus 3. Does this, if I cover these pieces up, can you tell it's the same thing that we started with? It's something squared plus the same something. Everybody cool with that? What is the c or the h value that I've chosen in this? 3. And because it was always x minus c, if I make the comment that, all right, just logically, if h equals 3, then how did this graph move?
Right.
3 units right. Now, normally we think about the parent function with these, and it's nice, but we're going to graph this one. What would I put in here? H of x in this case, did I put a number a in front of it? No, so I think that this must have just been f of x minus 3. There's that h value inside my argument. And it's weird to look at it, naming it a different function, but let's just see what happens. So we'll switch this up. I'm going to go back to Desmos, and then it was x squared minus 3x, right? Or x squared plus x? Okay, so here's the original. It's been moved a little bit. Something changed. Cool, we can deal with it. If I now decided to graph, okay, x, we'll do it two ways. We'll do f of x plus 3 minus 3, right? Okay, that's what it comes up to. And then we'll just double check. If I come back over here and I just try to graph a different one that says, oh yeah, let's just do x minus 3 squared plus x minus 3. Do we get the same graph? Now, this notation is new to you, I think. I don't think you've ever done the f of part, but is it any different than just plugging it in there? No, it makes it a lot nicer to rewrite and change stuff easily and quickly without having to write down all the ugly stuff. Everybody cool with this first one? Okay, I want you guys to answer the next one. This is you guys working together. We still have f of x is here, but this time I want h of x. I'm going to leave off this middle part. We'll do it the same. Ooh, I want negative 1/2 x minus 3 squared plus, and I'm going to make that minus 1/2 x minus 3. I don't want you to graph it. All I want you guys to do is see if we can't find what has changed about A, what has changed about C, or H in our case. And I should have used a different number than minus 3, but I've already committed. Cool. Remember, you're welcome to chat with each other. It might be helpful, maybe, to put this part here, but I want you to find it rather than me just give it to you. For me, it's way easier if I do it here first, but it doesn't really matter which one we go first. And then it's just, let's write that middle blank spot. Equal negative 1/2 f of x minus 3. How did I get what? So notice in that general form, Red, it's x minus h, right? What should I plug in for h so that it reads x minus 3? Like, what would you have to plug in for h to make it x minus 3? What if I want it to be x plus 3? Yeah, and then that would move me left. Yep, that's what's happening. Okay, a little harder, I assume. Now, maybe, I can't tell. Based on your facial expressions and lack of volunteering an answer, I would assume it's a little harder. Is there something I could factor out of both of these? Okay, if I do that, can you guys see that? I can't. If I factored a negative 1/2 out, then all I'd be left with is x minus 3 squared plus x minus 3. Everybody okay with that? Which, notice, was exactly what we saw a second ago. I think that that'll just be exactly f of x minus 3 again. That's a weird stretch. If you've never done this, did I lose anybody here? Okay, so I did not mean to give you the same one. It obviously moves which direction, how many? So 3 right. So notice, I just dealt with, when I'm looking at this, did I deal with what was in the parentheses first, or did I deal with the multiplication first? Did I? Did I? We said 3 right first, right? Correct, sorry, that's a terrible choice. I think I'm doing what's in the parentheses first. It seems like I'm following PEMDAS, exactly like we always do. What does this do? I'm going to need 2 comments, and these ones are interchangeable. First thing, what do you see about negative 1/2 out in front? I heard x. Can you be more specific? Reflect over x? Okay. That's that negative part, right? What about the 1/2? Vertical compress. So I'm okay with that. Vertical will compress, and this is a weird one. By what factor? So it's a strange one. I would say I'm compressing by a factor of 2, or I'm stretching it by a factor of 1/2. It's getting shorter either way. I'm just going to call it a vertical compress. Okay, now here's my challenge. I haven't put this one in here yet. Here is, and I'm just going to copy this one. What? Okay, that part's okay, the black one, I think. We can see this is what it looks like, and maybe we just needed this one instead. But if I wanted to reflect this, can we? If I just put brackets around everything, we'll do it here. What's our number? Negative 1/2? So it should get wider, right? Because we're compressing it vertically, and it should reflect. Let's just see if that's what happens. Okay, and I'm going to do this one, negative. Turn on. Hey, did it get wider? Cool. All right. Doable? Okay. Let's knock out only 2 more. Well, we did H and we've done A. What else do you want to change? K. I'm not going to say like much at all about K. K is 4, and I promise I know how to spell. This is the dumb way that I remember it. It's how I've always remembered it. K is for vertical, like every time. There's nothing crazy that happens with K. If K is positive, what do we do? You go up K. What if K is negative? Down K. Where parentheses live when you read an expression will have a huge impact on how you interpret stuff. I alluded a second ago that when we're working through these, inside the parentheses happens first, and then the multiplication, and then finally, what's, bless you, at the end of your order of operations? So parentheses and exponents, and multiplication, division, and then what are the last two? Addition and subtraction, my bad. Addition and subtraction. Which means where we put our parentheses around stuff really matters. And this can be tough to pick out. So I'm going to switch up. We're going to do another example. But what I want you guys to do is explain, or order, if you will, order these transforms. And let's do it from a parent function instead. From, let's say, f of x equals, let's do a little different one. Let's do x cubed. Okay, so I'm going to write an ugly expression here, and I want you guys to tell me what happened to move from the graph of x cubed to this new one. All right, so we have h of x equals, let's say it's negative 2 x plus 3 cubed plus 1. Sorry, I heard you say something a second ago, but I didn't grasp it, so I just chose to pretend like I heard. Cool. All I want you to do is tell me what happens. I'm going to get a rough sketch of x cubed up on the board on the other one, and I'm going to ask somebody here in a minute to come and help me graph it. When you guys look at this, what's the first change you notice? Ooh, it's not right though. Because remember it's x minus h. It would have had to have been x minus negative 3. So h is negative 3 in this situation. We go left 3. Now I heard somebody, I didn't really draw it out, but somebody said up. And I heard somebody say up right away. Notice I haven't written it yet because I want to look at it and compare. What's the next thing that you guys notice? So it reflects. I'm going to just say reflect over x and stretch. So vert stretch. And I'm not going to list the factor, but you're absolutely right, is by 2. So we've moved it left 3, we've reflected it, and we've stretched it. Last but not least, up 1. Does the order, like I've been alluding to, that it definitely does. Why does the order matter? What if I switched these two around? Would it change my graph? Yeah. Hugely, right? If we follow order of operations. The first one, you guys told me was left 3. it's going to be green. Left 3, right? There it is. Okay, and then we reflect it over the x. I'm going to stretch it. So here's the width of it, yeah? And this is that steep part that I was talking about. So it is wider or thinner. I know it's still going to have the same root because it's just been moved. Does that look like a steeper version now? A little bit?
Yeah.
I can probably make it a lot steeper. And then we'll do this last one in black. Now what? Up 1. So if I take this point and I just move it up 1, it looks like it should be about this. Okay, that's what we get if we do it in this particular order, the way that we're supposed to, following order of operations. The most common mistake that people make, and my eyes are drawn to it just like somebody else's were, I look at this and the first thing I immediately notice is it's gone up 1. Like that's the first thing that my eyes are drawn to. But if we had moved it up 1 and then left 3 and then reflected, this point that moved up would have wound up down here and we would have gotten this graph that's close, but notice it's in the very wrong spot. The order that we go in, it looks gross, it's just order of operations. Okay, cool with that. Sweet. Am I going too slow? Too fast? Okay. We only have one more to deal with. B. All right.
I remember we were in like 8th grade with Miss Jarvis and we had a problem like this and did it in the wrong order.
Oh,
And it
that's
took
how we got it
like
wrong.
none of us could figure out why it was wrong. That she couldn't figure it out. I think she asked you. Yeah,
I remember messaging Miss Jarvis about it while I was with baby Zeke because I was not in school at that time. But yes, I also have that vivid memory. I didn't know it was your guys' class. Yep, it's PEMDAS. That's it.
I don't remember the words you're stressing on.
Yeah.
I remember that.
It was something like this. You guys were doing it on this form though.
Yeah.
What happens first here?
The exponent.
Yeah, what if we did something like this? Ooh, I can't use that letter.
What?
Side X minus H and then
Yeah.
C.
So you do it moves horizontally and then whatever the C change here does, and then it gets steeper or less steep or reflects, and then it moves up. Yep, it is just order of operations. I've never seen that written down anywhere, ever, except for a new Algebra 2 book. It like explicitly says, here is the order of operations, which is pretty cool. It's a tie-dye book cover, yeah. Indeed it is. All right. I don't have a good alliteration for this one. B is for, now in trig stuff, when we graph the trig things, we'll call this a phase shift. You guys might remember loving that. B is for horizontal reflections. And you guys used a different word. Instead of me writing compression and stretch, dilation. Okay. Why is x squared a terrible example for this one? Yeah, and if somebody's listening and you go, what? What do you mean you can't really tell? I just want to show you something here. Let's do h of x this time is f of, pick a b value. Let's do -1. Okay, here's x squared. It's beautiful, right? Now notice the negative inside the argument this time. A lives outside of everything, B lives inside. What happened? Is it? Okay, it's hard to tell, right? The quadratic's a poor choice. I haven't changed anything, it's still f of -x. It reflects, so this one is weird because you could think x or y. This one is indeed the y-axis. And we can show that by if I just let this shift one little spot. Let's say it's x minus 1 cubed. Now it's really clear. It's moved right 1, and then this negative reflected it over the y-axis. So, just like we did before, reflections and dilations. The first one, reflect. It reflects over y-axis if what? Good. If b is less than 0. If we have a value inside, that's less than 0, then we reflect it over the y-axis, where things get super weird. And I'll just talk about it right now. Don't write this down. I just want to make sure we're aware of it. It is really common to see these things written like this. If this is h, can you guys tell me how this moved? And again, you don't have to write it. Let's just think about it. Anybody tempted to say it's moved left 1? Probably everybody, realistically. You're wrong. It's moved left 1/2. Why? I think you see it.
Oh, because you saw something, yeah.
If we wrote it in that b times x minus h form, this would turn into 2x minus 1/2. And now I can see, oh yeah, it's moved 1/2 units horizontally. And then whatever this is going to change, which we'll see this. It can be hard to pick out. This is way, way, way more common than the other way, but it's easier to teach it the other way. All right, so now we get all absolute value-y about this. If the absolute value of b is less than 1, and in your text it'll say 0 is less than that is less than 1, but we all know absolute values are always positive. If this happens, just help me out here. If b is absolute value less than 1, I'm going to go back to the nice one. X cubed. I'm going to get rid of that parenthesis. And let's just make it, we said less than 1?
Yes.
Okay, so give me a number less than 1.
0.5.
What happened? It's that same situation where we've already dealt with the up and down. If I'm going to make it wider without me taking the time to awkwardly climb up on the table, here I am, 0.5. If it gets wider, what way do I move my hands horizontally? I've stretched horizontally, which is weird because when we stretch horizontally, it makes our graph wider. You can see it when you physically touch it or see somebody doing it, but it's strange that the language just flip-flops. But check it out. If b absolute value is less than 1, then horizontal stretch. Now it's by a factor of b. By a factor of b. And I'm going to change this a little bit. I'm going to say 1 over b. So that if x is, or if b, for example, is 0.5 or 1/2, that's been stretched by a factor of 1 over 1/2 is 2. Twice as wide now. Okay, what's the other situation I'm going to say? Absolute value of b is greater than 1. Horizontal compress. It gets thinner in this situation. So we'll do the same thing that we did before. Did I use wide and narrow? I think so. Wide, narrow. Cool. As we look at these, 100% you legitimately could get by like all of Precalc and future math classes with knowing none of this. Just so you're aware. Like, you don't need any of this, but if you don't want to have to build a gigantic table every single time that you graph something, these are beneficial. This is an efficiency thing. Cool. All right. Yeah, I'm good with that if you guys are good with that.
Yeah.
Cool. All right, you get 12 minutes to start homework. It is pretty short today. And I wonder why it's so short. I don't remember. You're going to do a few graphs. If anybody wants graph paper, up in the corner there, I do have graph paper like on the other side of the bookshelf. Let's knock this out.
Are you doing like pretty graphs or like sketching?
I'm okay with sketching as long as they're not like way, way, way off. All right. So today, 9, 8. Lesson 1.7. I'll put the link up there in a second. Link. Homework 1.7. You will find waiting for you on page 72. You get problems 1 through 4. Yep, I'm good with these. 11 through 14. And 55 through 58. Okay, as I'm looking at it, you guys will be pleasantly surprised, I think. There's not a ton of graphing. I don't know if there's any graphing that you actually have to do. I think that I'm just going to, at least for now, trust that you guys know how to graph. And if there really are big issues, we'll see it when we get to the specific types of graphs. This knowledge will keep coming back. Cool. I'll let you guys 10 minutes.